Okay, so in this video, we're going to extend the discussion of springs and differential equations to now systems of springs and not just a single spring. So let's consider our first example. We have a mass here, mass 1, which is connected with a spring to a solid wall. We have a mass here, mass 2, which is connected to mass 1 with a spring, and then it's also connected to the solid wall on the other side with a third spring. And what we have is we're going to say the x-axis in the positive direction is our displacement in the positive direction. Now we want to find all the forces on each mass. And so the first thing that we have is the general relationship that F is equal to ma, and A is x double prime. And then in this case, if we assume that there is no friction, just to get us started, then the other force that is being applied here is Hooke's law, which is going in the opposite direction and is F is equal to kx or negative kx. Again, the force is applied in the opposite direction of the motions, and so we have this negative. Now, when one mass moves, that creates a pressure on the spring between them that then applies a force to the other mass. So we have to take that into account as we set up our problem as well. So let's consider mass 1 given by its position x1. Now the acceleration is m1 x1 double prime. And then to find all the forces, we have to find forces of motion from the spring on the left side and the spring on the right side. So the mass on the left is being applied with a force, spring constant K1 times the displacement of x1. And then there is a second force from spring 2, which is now also being applied, negative K2 times x1. Now, if we fix M1 and we imagine that M2 is moving, then this also is going to stretch the spring in the middle. And so then that's also going to result in a force being applied to M1. So that's going to add K2 times X2. Now, the third spring does not directly apply force to M1. So that'll apply to the position of M2. We'll get the system of interacting variables, but it's that application of force is only indirect, not direct. So our differential equation is going to have m1 times x1 double prime, and then the balancing forces on the other side are going to be spring 1's action on m1, spring 2's action on m1, and then the application of the force from the spring 2 from the action of m2. So that's going to be that interactivity between the two springs. Now we will set up the second one in a very similar fashion. The acceleration of the second mass is m2 times x2 double prime. That's the force that we're balancing. And then the forces that are applied directly to m2 by motion of m2 are going to be Hooke's law from spring 2 and Hooke's law from spring 3. But then when M2 is fixed and M1 is moving, that's going to apply a force from spring 2 based on the motion of M1. And so altogether, we have this behavior from spring 1 and then this behavior from spring 2 and spring 3. And that, again, has to add up to our acceleration. Now notice the signs, the motion of the mass that we're modeling has a negative sign in front of the Hooke's components, but it's applying in the same direction, not the opposite direction, when we're getting motion from the other variable, the other mass. And so that sign flip is consistent between these two equations. Now, again, we treat these as vectors and we solve for x double prime as a vector. And so we're going to end up with, I'm collecting the coefficients of x1. This is my matrix. There should be a x1, x2 vector out here. But these are the coefficients of my x1, and these are the coefficients of my x2. And then this is the coefficient of my x1 in the second equation, and these are the coefficients of my x2 in the second equation. And so this is essentially the A matrix for my system for x double prime. And then from here, I can then try to solve this using, my linear algebra methods. Now, before I solve for this kind of a situation, I need to solve for, okay, so what happens if I have damping on the model? How does that work? So now here is another example where now I have some damping being applied. Now this is being visualized as a dashpot type mechanism, but you can also imagine like this being inside a fluid or something like that, where sort of the general sort of atmosphere is what is actually causing the damping. Now, in this case, we have this damping force that's given by a gamma times the velocity being x prime. In this diagram, they're using B1 and B2 for these gamma coefficients. Now, the springs, the Hooke's law and the acceleration are still going to be applied. But in this case, we also have to add the damping components. So if we think about the damping motions from, or any of the motions from motion of M1, then we get, in this diagram, we don't have 3 springs, we only have the 2. So here's M1 and it's moving. We get 1 spring that's going to give us motion, again, in the opposite direction to the motion, a force applied here. If M2 is moving, then that is going to apply another force, as we saw in the previous example, to M1 because of the motion of M2. And if there is damping between them, then that is going to be affected by both the motion of M1 and M2 relative to each other. And so we end up with this final expression where the damping comes in with x prime, x1 prime, and x2 prime. And then also this results in the motion from the springs. Now, if we look at the second mass, we will get a similar relationship. If M2 moves, then we're going to get 2 springs acting because this mass does have 2 springs applied. So we're going to get interaction from both the motion of M2 because of the action of spring 1 and the action of spring 2. And when M1 moves, that's also going to apply a force to from spring 1 to mass 2. And then we also have this damping between the mass and the wall. And we also have the damping from the motion of mass 1. And so when we put that all together, we have our 3 components: motion of mass 1 on the first damper, and then motion of mass 2 from the first damper, motion from mass 2 on the second damper, and then spring forces from the motion of mass 1 and spring forces from the motion of mass 2 on both springs. Now, in order to solve this one, we don't have that. In the previous example, we didn't have any x prime terms. We just had x double prime. But here we have x prime terms. And so in order to make this into a fully linear model, we have to make some substitutions. We're going to let x1 prime become x3 and x2 prime become x4. And then x1 or x3 prime will become x1 double prime, and x4 prime will become x2 double prime. And so we start solving our 2 substitutions, and then on this side of the equation, we replace x3 prime for x1 double prime, and we replace x2 double prime with x4 prime. And then the rest of these equations also get these two variables swapped out. And then our third and fourth equations are just these two variables that we are using as our substitutions. And now, again, we can divide out the masses and then collect coefficients for our various variables in the equation. And that will produce a matrix. Again, these are our first derivatives now, 1, 2, 3, 4. And then this is our x vector is our set of x1, x2, x3, and x4 variables. And these are the resulting coefficients. The first two of these are just x3 is equal to x1 prime and x4 is equal to x2 prime. And then these are all of the coefficients from our system that we were looking at with the two springs and the two masses. Now, if you have springs that are connected to each other in various ways, then those coefficients without masses in between them, then those coefficients can't get added sort of directly to each other. So if you have springs like this in series, you would add them into as a coefficient in the equation in this form. If they are in parallel like this, then you would kind of just add them directly. Now, in most of the cases where you're going to, at least initially, start to see these kinds of systems, these circumstances are not necessarily going to be the first ones you encounter, but it is worth knowing that when these get coupled like this, they're going to behave in slightly different ways. And you can't just, like the ones in series, you might be tempted to think, oh, I'm just going to add them, but that isn't quite how it works when there's no mass in between them. Now, if you are going to actually do a model with one of these in them, so here we have them working in parallel, and then here we have one that is working in serial, then when you put your masses together, again, think about how these springs are coupled together and how those would go into your equation as your coefficients. So again, treat these as if it were a single spring, but with this parallel coefficient like so. In this side, you're going to treat this as a single spring, but then the coefficient is going to be given by this series equation. So you will have to substitute in the values and then calculate the resulting force of the spring. And then you can, again, in this case, if this mass moves, we have only a single variable going on because there's only one mass, so one x position to worry about. And so we will get an actually much simpler expression. This isn't a system of so much as a system of springs as it is a situation with very complex spring behavior. Now, if we want to consider a further extension of systems of springs, then we want to consider not just a one-dimensional system of springs, but a two- or three-dimensional system of springs. And this is going to allow us to model things like crystal bonds or molecular structures by having these complex relationships. Now, we're not going to be able to go into the full set of the kinds of models, but I wanted to just walk a little bit through how we would make these extensions. Now, for each one of these components, we're going to, for the moment, we're going to pretend that all of these masses are just one, just for the sake of simplicity, so that they're all equal. Obviously, in a crystal structure, that would only be true if all of the molecules, all of the atoms were identical. But for here, we're just going to simplify it a little bit just for the sake of talking through the concept. Now, in a two-dimensional model like this, you're going to have action from this spring on the y coordinate, and you're going to have this action from this spring on the x coordinate. And if you're in the middle of the lattice, you're going to have two springs acting in the x direction, in the y direction, and two springs acting in the x direction. And their neighboring components are going to affect them from either side, or above and below as well. So let's look at something like this position right here, M22. So our subscripts match our position in the lattice, and then our X22 double prime. And what we have just in the X direction, again, just think about it in this direction, we're going to have the motion from this spring affect as this one moves, that spring is going to have an effect. As this position moves, this spring will have an effect. But if this particle also moves, X21, then that spring is also going to have an effect on that. And if this particle moves, that spring here is also going to have an effect based on that motion. Similarly, if we were looking at it in the y direction, M22, Y22 double prime would have an effect if this particle moves from this spring and this spring. And then also, if the particle above it moved and the particle below it moved, then you would also have an impact from the motion of the particle above and the motion of the particle below. And then you would have this all in interior, all of the equations in the interior would look like this. All the equations on the exterior would have, like this one would have only 3 of these relationships, not 4, because there's no spring out here. If you're over here, you're only going to have 2 of these, one from this particle on each end, one from this one, or this spring as this one moves and that one moves in the x direction. So the equations will be simpler, but they will be set up with similar logic. And then, of course, keep in mind that these are moving in 2 dimensions at the same time. And so you're going to have motion in both x and y directions. If you had a 3-dimensional grid, you might have a layer on top of this, and then you would have a similar set of equations in the x direction. Now, in this example, we're assuming that all of the action is taking place essentially at a right angle. So the x springs are only affecting the x direction, the y springs are only affecting the y direction, and they don't change as the angle changes. If you get a much more complex crystal structure, you may have something acting at sort of an angle to each other, a bond with like the next layer up and one particle over. And then, of course, these models can become much more complicated. But these combinations of spring models are essentially the concept behind, at least the foundation for starting these more complex interacting spring models. How would a grid like this jiggle, and how would those forces affect other particles in that structure? So again, as you go on through physics, I have taken courses where we did actually have to do this, but if you're just in differential equations, I think it's just a nice insight into sort of where you can take this, where you're going.